Welcome to qnawire.
All right, we have a CFL. Bulb, right? And it contains 1.4 milligram of mercury. Okay. And the question is, if each mercury atom emits a single photon with a wavelength of 254 nanometers, how many joules of energy do we get? All right. So the question really is, how much energy is in a single photon? When that photon is 254 nanometers. And then how many photons and then multiply the energy in one photon by the number of photons. That's our task, really, right? And when it comes to how many photons, we're told that we get one per atom, right? So this is also equal to number of mercury atoms. Okay. So we say number of mercury atoms at 1.4 milligrams, energy per photon when that photon is 254 nanometers, and then multiply those numbers together. So let's start by figuring out how many mercury atoms we have. So we're told that there's 1.4 milligrams. Well, we need the molecular weight of mercury, right? And that is that there are 200.59 grams per mole of mercury. Okay. And if we have milligrams, right, and we want to figure out atoms, we may want to just figure out moles and then convert moles to atoms. Okay. Another thing we're going to need to do here is the molecular weight of mercury is given in grams per mole, so we need to figure out what that is in milligrams, right? And the conversion between grams and milligrams is that there are 1,000 milligrams for every gram, right? So if we take 200.89 grams per mole and say 1,000 milligrams per every 1 gram, grams will cancel and we'll get milligrams. We'll get whatever this is times 1,000. Okay, so we're going to get 200.89 times 10 to the 3 milligrams per mole. Right, 10 to the 3 is the same as 1,000. Okay. From here, move this further down. And we're still looking for the number of mercury atoms that we have. Now we know how many milligrams are in a mole, and we know we have 1.4 milligrams mercury. So what do we need to multiply to convert milligrams into moles? Well, if we divide by the molecular weight, that's like saying 1 mole per 200.89 times 10 to the 3 milligrams, right? This should tell us how many moles of mercury we have. And if we're not really interested in moles, but instead interested in atoms, then maybe we want to say, okay, in 1 mole, how many atoms are there? That's Avogadro's number, 6.626 times 10 to the 23 atoms per mole. Okay. So now milligrams will cancel, moles will cancel, and we'll be left with atoms. Avogadro's number, this seems like the wrong, yeah, I gave the wrong constant, 6.022. That was like a version of Planck's constant. I need 6.022. There we go. Okay, so now let's just do the math on this. It's going to be 1.4 4 divided by 2000.89 times 10 to the third times 6.022 times 10 to the 23rd, and we get 4.197, or we should say 1967 times 10 to the 18th atoms of mercury. Okay, so now we know how many atoms of mercury we have. Next, we need to figure out how much energy is in a single photon, right? When that light is 254 nanometers, right? So the equation that we're going to use here is that energy is equal to h nu, where nu is the frequency, and this is the Planck equation, right, where this is Planck's constant and this is the frequency of light. Well, if we don't know the frequency of light, right, what's the relationship we have between frequency and wavelength and light, right? So remember that the frequency of the light times the wavelength of the light is equal to the speed of light. Or we could say that the frequency of light is equal to the wavelength, is equal to the speed of light over the wavelength. Right, there's a little bit of algebra here, which means that the energy is equal to hc over lambda. Okay, so Planck's constant times the speed of light in meters divided by the wavelength in meters should tell us the energy of a single photon. Okay, well, now we know how to get the energy of a single photon. So let's move some of this out of the way. We have some more space. We've got the number of atoms here. Okay, but what we need is Planck's constant. Here's that 6.626. 6.626 times 10 to the negative 34. Ooh. Oh, I see what I'm doing. Joules times seconds. Okay. And then the speed of light is going to be 2.9998 times 10 to the 8 meters per second. And then our wavelength, right, is going to be 254 nanometers, but we need it in meters. So how do we convert nanometers into meters? Well, there are in 1 meter, 1 times 10 to the 9th nanometers, right? The nanometers will cancel and our answer will be in meters. Okay, so we can just simply put this into a calculator now. 6.626 times 10 to the negative 34 times 2.9998 times 10 to the 8th divided by 254, and then that 254 is over 1 times 10 to the 9th, so we could say 254 times 10 to the negative 9th. And finally, we'll get an answer of 7.825 times 10 to the negative 19 joules. And that's joules per photon. Okay, so now we do 4.1967 10 to the 18th photons times 7.825 times 10 to the negative 19th joules per photon. And what do we get? I get 3.284. Joules.